Now, dear students, let's have a discussion on sharing of electrons and and to try to have some insight into the quantum mechanical view of having a covalent bond between two hydrogen atoms. And what we would like to start with is that uh, we have H2 uh, gas molecule, and it has lost one of its electron. So it has only one electron. So this will be the point of discussion here in this video, and the hydrogen molecule ion we have here, and we have a single electron that bonds these two protons. So you have two protons, and there is a single electron that makes a bond between these two protons, and if we talk about the protons, what's going to be interesting here is that if we go back to the concept of particle in a box, if we had a box of whose potential wall is infinite, the wave function had no probability to be found on the other side of that wall. But if the size of this potential of this wall is finite, then we could find that there is a finite probability that the wave function could exist on the other side of the ball, even though the probability of having wave function on the other side is extremely small. So so to say here that if the ball is infinitely strong, the wave function is exactly inside the box. Now we have these protons, and there is electric field around these protons. And this electric field is exactly acting it has an effect like that of a box of an electron. And two nearby protons that we have here, they correspond to a pair of boxes with a wall between them. And uh, and 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 no mechanism that we have in classical physics that can permit this electron to that can permit this electron in hydrogen atom to jump spontaneously to the nearing proton. Uh, so that's not the case. The classical physics, for the classical physics, this what I call as the barrier that is here for the electron with respect to these two protons is large. So classically, for this particle, this electron cannot have any probability being on the other side of the nucleus. And if we try to understand the problem, and if we go with the potential that we will have with these two protons, it will be something like this, and 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 like this, and then you will have something like this. Now what can I say is that this potential is due to the proton, say alpha, and this potential here is due to another proton, say beta. And between these two particles there is a separation, and this separation is, say, r. Now, uh, the electron can be anywhere, and if I have to talk about the energy of electron, this will be the energy of the electron, and we can see the potential. For this potential, classical mechanics has no explanation. The electron has no chance to be on the other side of this potential. So to say, so to say, what can be, how can we have a proposition on this problem? Uh, and so classical physics does not permit the electron in the hydrogen atom to jump on the neighboring proton. which is more distant than its parent proton. But quantum physics has a solution. Quantum physics has at least an argument. And what's that? Such a mechanism where the particle's energy is less than that of the wall. It certainly exists in quantum mechanics. So certainly there is a certain probability that an electron that's trapped here in one box will tunnel. It will tunnel through the wall and get into the other box. And once there, it has the same probability for tunneling back from the position, say classical position I'm trying to take here. It has the same probability to tunnel back to its original box. Now, this is what we have been trying to demonstrate in this diagram. Now, in order to be sure that an electron will pass through the region of high potential energy wall, we can see here the wall that's between the two protons. It certainly depends strongly on how far these two protons are apart from each other. Now, if the proton-proton distance is nearly 1 angstrom. If this is the case, the electron may be regarded as going from one proton to the other proton in a time of the order of 10 to the power of minus 15 seconds. So we can understand how fast. And we can legally consider such an electron as being shared by both the protons. Now, if the proton-proton distance is if the proton-proton distance is nearly 10 angstrom. Now, in this case, the electron shifts across across an average of only about a second. And if we have this much of distance between these two protons, and if we consider the same quantum mechanical considerations, the electron is going to be on the other side in 1 second, and this 1 second is very, very large, and it's extremely large at the atomic scale, which is practically infinite. If I say 1 second here and 10 to the power of minus 15 second, when the distance between these two protons is 1 angstrom. So it's like this time is taking infinite time with respect to the time that was in the previous case. Now, the effective radius, if we talk about the 1s wave that we have, the 1s wave function in case of hydrogen atom, it's nearly 0.53 angstrom. And what can be concluded from here is that electron sharing can take place only between atoms whose wave functions overlap, and the wave functions should overlap to a very large extent. So they must be close to each other. The two protons must be very close to each other. So the two protons can share, and we haven't, and we can say why the energy of such a system could be less than that of a separate hydrogen atom and a proton. So we have a case of a separate hydrogen atom and a proton here. It has an electron. Now, certainly, the total energy of these independent particles is more than that of the energy that this H2 plus molecule has. So this is certainly consistent with uncertainty principle. This is because the smaller the region to which we restrict a particle, the greater must be its momentum, and hence it must have large kinetic energy. So to say that what we have here is that that the distance between these two protons is a matter of concern, and that becomes the basis for the sharing of electron, this single electron that we have considered in this case. So to say that two protons we have here, they are confined. They are confined to one another by virtue of this single electron, and what it means is that taking into account the uncertainty principle, that the kinetic energy of this kind of system, where we have the sharing of two protons, by virtue of Heisenberg's uncertainty principle, is less than that of the energy of this hydrogen atom and a single proton. So this could be the reasons of this could be the basis for covalent bonds that we have, where we have mutual sharing of electrons between the two atoms, and this mutual sharing can only be explained by virtue of the tunneling that we have. The tunneling, that this electron has a probability, no matter how small, to tunnel through this potential barrier and keep on tunneling from alpha to beta, beta to alpha, alpha to beta, in a very, very short span of time. And at the same time, if this distance goes large, then the time of transition can be large, where we can say that no sharing of electron has been taken place between the two atoms.